Sorry about that. Okay, so this is a little group project we did last semester, which arises from, you can see, from the number of people who are local. It's actually arises from a local AstroPH discussion. And actually, I'm kind of nervous. I usually don't get so nervous. I'm a tenure professor. I've been giving a lot of talks, but I see a lot of 425 students here. And I've been criticized for my talk relentlessly for the past semester. You get to see how I do talks. Okay, criticize. Okay, so I'm interested, in this particular talk, I'm going to talk about binary stars. Sorry, before this is all messed up. How do I get rid of everything? Second. Okay. So I'm going to talk about eccentricities of binary in particular, and how the distribution of a bunch of binaries look like in eccentricity space. And in this slide, I'm like motivated with three possible distributions of eccentricity. The first possible distribution is actually the red line. Okay, the differential forms here. That's a differential form and it's cumulative form. This particular form is called a thermal distribution. It's thermal. Why is it called thermal distribution? As you can see here, that in this particular form, there are a lot more binaries of high eccentricities and low eccentricity. The probability goes up with eccentricity. And it's called thermal because when people do simulations, what they do is that they have n-body systems and that n-body kick each other until in the end you're left with two stars. Binary stars, they usually end up with this distribution. So it's called a relaxed situation. Why is it in relaxation? Why there are more binaries are high eccentricity than low? It's because in high eccentricity there's more phase space. Because you think about it, eccentricity is a vector. It's a two-dimensional vector. We're going to come back to that later. And so a large eccentricity so has a bigger circle. So it encompasses a bigger circle. So relaxed state has more bodies there. That's super interesting. That means if you see the distribution like that, that means that whatever binaries you're looking at have undergone a lot of this kind of dynamical bombardment, dynamical relaxations. Not only they get heated up in eccentricity, they probably also get dissolved. So whatever binary you're seeing now will be just a little remainder of the previous historical event. There's another kind of possible distribution, which is called a uniform, the gray boring bar there. That means if you form a binary, the eccentricity is an irrelevant dynamical quantity. That's why it's flat. Okay? Hopefully nature doesn't give us this because that gives us no information. The thermal also gives us pretty little information. The best distribution is the green one. If you find that in reality binaries have distribution which have a hump, this is really good because you can measure this, that gives you a number, which you can quantify different binary populations, and that is informative. Okay? So we really want to get the green one, and we don't know what nature will give us before we start. So I want to introduce one slide, is what binaries look like. It turns out half the stars, at least for the sunlight stars, half the stars in our neighborhood or in the universe too, are in binaries. They kind of distributed like a green curve in periods, if you just look at how separately they are. This is sort of the frequency of binaries in periods, and we call it log normal because it's the logarithmic space. Okay, you all know this system. This is the closest binary or closest star actually to us. Proxima Centauri is the little one up there. It's actually in a triple star system. Proxima Centauri is quite far from the other two stars. And the separation is about 8,000 AU, which puts us around here. So it's a wide binary as far as we're concerned. Okay? And then the Centauri itself, the Centauri itself has two stars, more massive, and they're about 23 AU. I put them on the closed binary section. Obviously, we have so many binaries in our neighborhood. You can just keep on collecting them, keep on measuring the eccentricities and so on. So when you have the period distribution, you would have thought by 2025 we know eccentricity distribution. The answer surprised me when I started looking into this, that we don't. We do know that Y boundary tend to be thermal distributed, which is consistent with the fact that they've undergone a lot of dynamical interactions, passing by stars, hitting them, and that kind of thing. But close boundary turns out, surprisingly, not known. This is an annual review article from 10 years ago. This is an eccentricity, that's a thermal, that's a uniform that I talked about before. You can see that the green curve is what we know about the neighborhood, solar type binaries. You can see, if you see a accumulated curve like that, and you see a bump jump like that, that means the sample is really, really small. So there's only a few dozen samples in there, which surprises me, because we know thousands of spectroscopy binaries, and this is using those thousands of binaries. And then you can now start saying what that distribution looks like, but I can guarantee you that's wrong. Why is that wrong? As being remarked by the annual review article here, that there is a strong bias when you're trying to get eccentricity distribution of even nearby binaries. There's one particular bias is that if the binaries, which is now being observed in radio velocity continuously, if it's a very eccentric, so spend most of the time in the epicenter, where it causes very little RV variation, by the time it sweeps by the pericenter, it's really fast, so it's hard to catch. So as a result, there will be a lot of bias against detecting high eccentricity binaries. All the dotted lines here, all these lines for different types of stars is caution that we should not trust any of this data. But what about the green curve? Should we trust that? The bottom line of this graph is that despite decades of work, laborious, very persistent spectroscopy follow-ups, we still don't know eccentricity distribution of solar type binaries. Okay, obviously Gaia is the savior for many people in this department, and also for me. Turns out Gaia has observed about 1 billion stars, astrometric solutions. So about out of 1 billion stars, you should expect half of those binaries. So Gaia should have 500 billion binaries, and the idea is that, well, that's got to be a big enough sample. It turns out at Gaia DR3, which is about a couple of years ago, we have only good astrometric solutions for only about 140,000 main sequence binaries. Okay. Can you get the eccentricity distribution using 140,000 binaries? I would say yes. So that's what we're going to do. I was actually looking at this particular graph when I was studying the Gaia data. Janos, who's not here, I think Janos and I were actually interested in a different problem. We were interested in tide raised by binary on each other, and the dissipation of that tide. As you can see, the binaries are very close, few days and so on. Their eccentricities are compacted down to circular. That's because tidal dissipation. So we were actually interested in how can we use this to understand the tidal process, which is a theoretical problem I continuously bump my head against over the past 20, 30 years of my career. Never solved it, so I thought I'm going to use Gaia binary to solve it. We still can't, but we made some progress. But if you notice is that this graph shown here only goes to 40 days. Gaia binaries, Gaia has been up the sky. It just finished operation last week, something like that.
2 weeks ago.
2 weeks ago, but then it's been out the sky for 10 years, over 10 years. And Gaia DR3 includes binaries all the way up to 1200 days. So there's a big phase space from 40 days to 1200 days, which I wasn't looking at because I wasn't interested in it. But I decided to look at it anyway.
I really don't like 1 year. Guess
Yeah.
why?
You know why there's no binary here? So by the way, this is a kind of density, which means it's very dark, it's a model of systems, and it's very light, it's no system. So first you can see that those are the tidally circularized ones I was talking about. They're really different. They're no longer primordial. They modify afterwards. This one's probably primordial, okay? But there's a lot of data gaps. That guy has not really complete. There's different detection methods and all kinds of things. If you look at this, what do you think that distribution looks like? Is it thermal? Remember what thermal would be? I'm sorry if I'm taking you as my student. Thermal means heavy here, right? It's definitely not thermal. It's also not flat, it's something else. It's a trivial exercise to turn it into numbers, so just focus on the black curve. That's a differential distribution, the black curve on both sides. We have some distance bias we have to worry about. And gray, there's an underlying very light gray which you can't see. That's a theoretical curve called Rayleigh distribution. So we got our jet lag. It turns out binaries have a preferred scale. Something that I said was very good because I can actually extract information about the binary histories. Surprisingly, it's Rayleigh, and it's the most surprising thing for me was whenever I tell this to people, people said, really? At 2024, we don't know about binary eccentricity distribution? It makes me worry that there's something wrong. So I actually have to go back to a lot of literature to understand why is it we have not been able to do that until today. Regardless, when you actually do the fit, you find that it's a Rayleigh distribution. There's a very easy to remember mode, 0.3. And we try to get, because there's so many binaries in here, we can split it into many different samples. We can split it by the primary star's mass, by the periods, by everything. Every time we split it, it always returns that number. So since a very universal number, another way to say is that binaries in the Milky Way all know about something, the same thing, something that we don't know about. They all know that they all went through the same process, which gives them the same Rayleigh mode. That's the remaining on top. I would like to tease that with that single universal process. Yes. Okay. Oh yeah. This is to confirm that yeah we are. So we tried this for many different possibilities. For example, we also like to understand how this Rayleigh mode depends on the metallicity. Abigail is doing something on that. How it depends on the periods of the binaries. How it depends on mass ratios. This is period distribution again. The guy at the R3 is only sensitive to this little yellow band. Okay, we are very, as you can see, we have a very narrow window to the universe. We're hoping for a guy at the R4 and 5 to give us a bigger window to tell us what's happening here. Does the Rayleigh distribution smoothly transition to thermal, or is it something else? We don't yet know. I thought it was also amusing to plot, since I'm a planet person, it's also amusing to plot planet distribution. This is the eccentricity distribution of massive Jupiter. If you do a Rayleigh fit, it also gives you roughly 0.3. So maybe planets also know about something, just like stars do. Any questions up to now? Am I going too fast as I know?
So Rayleigh is just two Gaussian numbers squared and added together. Is that what
Okay.
you like to do?
Thank you. I didn't count that. So by now you should start asking what's special about Rayleigh. I'm sort of brainwashing you to say Rayleigh everywhere. But what's special about Rayleigh? It turns out Rayleigh is special. This is what's special about it. If you have two variables, which is both are Gaussian distributed, universe objects have always a normal distribution. You learned that from central limit theorem. So let's say one of the x is normally distributed, y is also normally distributed. So this is x versus y. Here's the origin. So x is normally distributed, y is also. If you take the radius of this distribution, if you take the radius, which is x squared plus y squared square root, that radius is Rayleigh distributed. Why do I want to bring this in? By the way, for students who are not familiar with this, but more familiar with this, this is something you see in your statistical mechanics studies. If you have three variables, all three of them are Gaussian normal distributed. If you take the radius, you end up with Maxwellian velocity distribution. See, one dimension higher if you want squared, you can start doing what if it's a 4D Gaussian, 5D Gaussian, whatever. So what's special about radiation? Radiation happens if you have two components which are uncorrelated, and each of them are normal distributed and not with the same norm. That's exactly what eccentricity can be thought of, because eccentricity is vector. So you can think of it having a x vector, x component and a y component. If there's some dynamical effect which perturbs this x component independently from the y component with the same effect, so it gives you the same norm, then you're going to end up with a radial distribution. Okay, that was my sort of starting point to think about this problem. But I don't know what could possibly be kicking stars. Think of this. These are two pretty massive objects, right? They are going around with some orbits, and what could be such a strong force that kick the eccentricity up to 2.3? So that's a pretty strong velocity kick. It needs to be something very massive. What could be in the binary system? I didn't have a solution, and for 2 months I just struggling with it by myself silently until one day in November, I think, I wasn't sure which day it was. We were having our usual daily arXiv discussions, and it was a low day. There was no paper. Interesting. Actually, there were cosmology, but the whole world is that's right. We should have more cosmologists to come to us to educate us. So we were here discussing, and I gave my conundrum to the crowd there, and to say, what do you think could possibly kick those closed boundaries to give them eccentricities? And Chris Master, who was sitting there as usual, and told me about this new paradigm in closed boundary formation. It turns out closed boundaries and Y boundaries are not formed the same way. As I told you, Y boundaries form some n-body system, we just kick each other and so on. Fragmentation forming n-body system, okay. Closed boundary, on the other hand, over the past, decades or so, people are now starting to believe they form this way. Okay. This is a simulation of, this is mass of a star, so don't worry about it, maybe just look at this column. If you have some stars being formed, and there's enough residual mass around it and momentum as well, it's going to form some massive disk around the star, protostellar disk. If you keep on increasing the mass of the disk, so like half or so, turns out, it would start gravitationally fragment, so-called Truman criteria. It's named after another white male. And those gravitational collapse, if you look at them in detail, you see that they don't necessarily exactly form two stars. They don't form a binary system right away. In fact, there can be multiple seeds of fragmentation. And then those seeds may combine, they can merge, they can also scatter out each other, and those could excite eccentricity. So that excited us to start the next stage of the work, is let's try and understand what kind of mass, what kind of companion you need to scatter out to get that 0.3 radial distribution. Sam did a very fast sequence of simulation because he happened to be working on something else related. And it showed up that if you want to generate 0.3, you scatter away brown dwarfs, which is fine, you can scatter away brown dwarf, but the brown dwarf all have to be anywhere in the galaxy about 1/10 of the mass of the binary star, of companion star, to be precise. Does this golden 1/10 has to be satisfied to get that 0.3. And the moment our simulations are not good enough to predict this is true or not, we don't know, theoretically. But you can say, well, what about, let's look for those ejected brown dwarfs. Do they exist? Can we see them? The answer is, of course, it's there, because astronomy has so many unknowns. If they go there, indeed, there are, turns out, there are lots of brown dwarfs in young star clusters. In young star clusters, it's easier to see those low mass objects because they don't have nuclear burning, so they dim with time. And they also are lower mass, so they get ejected from the cluster with time as well, evaporated. So if you go to young cluster, you can see the mass function. This is the mass versus the number. You can see this is the initial mass function. I got crude or whatever. But then there's a excess.
Just one of those ones.
See that? Another one.
Shower ray, but yeah.
Shower ray, another one now. Again. There are reported excesses of brown dwarfs. Is this the ones we're looking after to excite eccentricity? I don't know. I very much excited when we first came up with the idea, and also the empirical evidence seemed to suggest such brown dwarfs do exist. And in fact, the number of these brown dwarfs, if you count it, you know how many binaries there are, you know how many brown dwarfs you need to eject. If you count this brown dwarf, it's about right. It's about one system eject one brown dwarf. So seems plausible, but is that the right answer to explain binary eccentricity? This is my last science slide. Unfortunately, things are not so simple. This is another piece of physics that came in to complicate the picture. So over the past decade, there have been lots of numerical simulation which turned up surprising results. Okay. I think some of you joked to me before that there's nothing new in numerical simulation. Everything we know from analytical theory. Okay, this is a counterexample. It turns out analytical theory of this particular system, which is a circumbinary disk. Imagine you have a disk around two stars, a binary disk. Okay, and you ask those two binaries going around each other in the second binary disk, are their orbits going to change? For example, are they going to sink in by dynamical friction? Or is the orbit eccentricity going to circularize with time? Your physical intuition, I hope, as well as simple, hanging arguments suggest that they are going to sink, they're going to circularize, okay? Numerical simulation suggests otherwise. For example, in this case, red, this is the mass ratio versus eccentricity. For example, if you put a binary so that, this mass ratio, this eccentricity, red means they actually expect. We don't understand. Okay. The arrow here means that they're actually going to grow in eccentricity. This is a very interesting area of research which I have not been able to understand much, but now this could also potentially provide answer to the puzzle that we have, the Rayleigh distribution. And I think it's also should we have broader interest than just binaries, because if you think about binary black hole in AGN disk, or if you think about Jovian planets going around the star, all these dynamics could come in. So that was a twist which prevents us from solving this problem from beginning to end. But let me conclude here. My first takeaway, for me anyway, is that don't throw away data. There's so many good data in the DIA and any other data catalog. There are a lot of interesting mysteries. We found out from this simple exercise, I'm really bad at statistics. So without any formal statistics, we were actually able to get pretty interesting results, and we find a universal Rayleigh distribution. There's some dynamical reason to believe that this, because it's Rayleigh, it could be due to some kind of kick by massive companions, brown dwarfs, perhaps. But at the moment, we don't know. There's another possibility of second binary disk. And I'll end with this last conclusion. You're all welcome to our little discussions. Okay. Thank you.
We've got a couple minutes for questions.
I guess there's the inclination vector too, but it's probably much harder to observe.
The inclination vector is just complete initial condition, so we cannot really, there's no preferred. We cannot use that as
I guess the other question I had for this is, there are rare people in the 19th century just looking for hundreds of years. And not so many, but there are lots of visual binaries that have been measured. So is there any?
So the visual binary, go ahead, your question.
Well, we're just on the time scale of tens of years. I guess that's what they have seen.
Those are included in the SP9 catalog.
Okay.
Yeah, those catalog includes, works back to centuries of visual binaries and stochastic binaries. Yeah. Unfortunately, it's just not enough to actually get to the right distribution.
How many of these binaries are actually in a binary books?
Good question. Once we published the paper, some people wrote us to say some of the binaries actually are in triples. This is called compact hierarchical triples, which makes it very interesting because they can be used to test the theory. So it's about, I think the standard number for those triples is about 10, few to 10%. Yeah, so then you can ask, can the triples coexist with, yeah, that's one thing I promised the guy to think about. I haven't. If you want to think about it, it will be great.
There's a question left. And then
Is it possible these binaries are forming in clusters, so you're getting something like dynamics that's actually hardening the binaries?
Yeah, exactly. Yeah, so that definitely happened. Stars are forming clusters, and it turns out all the Y binaries have most likely undergone interaction in the cluster. But you can show that for close binary, less than 50 AU, they have very little influence.
you have a question?
Yeah, so I have a stats question.
Stats.
So Rayleigh distribution formally has no probability density at 0. And I'm curious about how much you care about actually characterizing the distribution of very low eccentricity binaries.
Yeah. Okay, so you're meaning are there any circular binaries in here? So you're asking?
Yeah,
Yeah,
I mean,
so
like if you look at the
rate
black,
distribution should go to 0. Yeah, should go to 0, and there's a little bump here. Yeah, but we actually look into that carefully to understand why is there a bump there. It turns out it's Gaia systematic. Is that a question you have? Yeah, but I also would like to comment, it's too bad this color this gray curve didn't come up. Well, actually many bins here are statistically inconsistent with rate. Too many outlying bins in this distribution, and I don't know why.
Yeah, and I mean,
If you have large enough sample to schools, yeah, it's not.
there's also just a physical argument that I feel like it feels a little unphysical to expect there to be no binaries with very small eccentricity.
Well, so that means they all universally undergo the same process.
It's the same as saying that no molecule in the air is standing still, right?
Are you asking why is it? Oh, you mean asking why is it go to 0 here? Oh, okay. So that's a different question. Sorry, I didn't understand your question. That's a different question. So that's just because if you take the radius, the probability of anybody living in this small radius is very small. That's why probability is 0. So similar to Maxwellian distribution, why there's nobody, why there's nobody sitting at 0 velocity, there's a probability of that's very small.
All right, we're at the hour, so let's thank our speakers.